In this video, we are going to talk about the various modes that any symmetric block cipher can operate in. Now, in order to use a block cipher in a variety of applications to achieve confidentiality and authentication, the National Institute of Standards and Technology, NIST, created various modes of operation for symmetric block ciphers. Now, these modes of operation work with any symmetric block cipher and not just advanced encryption standard or data encryption standard. So how many modes of operations do we have? Well, initially it was only 5, but today NIST has approved 14 modes of operation in a series of special publications. Now, there are 8 confidentiality modes, namely ECB, CBC, OFB, CFB, counter, XTS, FF1, and FF3. Then CMAC, that is used for authentication, code calculation, and then 5 combined modes that, when used with any block cipher, offer both confidentiality as well as authentication. These are CCM, GCM, KW, KWP, and TKW. We are going to look at 5 popular confidentiality modes, namely ECB, CBC, OFB, CFB, and counter. We will also look at CMAC, which can be utilized when a block cipher is to be used only for authentication. And then we will look at 2 combined modes, namely CCM and GCM, both of which provide confidentiality as well as authentication, and they are widely used today. So let's first look at these 5 classical modes of operation that offer confidentiality. The electronic codebook mode, or ECB, is the simplest and the default mode in which a block cipher operates. This figure shows how the encryption works in ECB mode. So you would split your plain text into blocks of equal size. For instance, in AES, you will have multiple blocks of 128 bits each, and in DES you would have multiple blocks of 64 bits each. If the last block has fewer bits than the block size, then you will add padding. Here, P1, P2, and P3 represent plain text blocks. Then you take each plain text block and encrypt it separately using the same cipher key to get a ciphertext block. So C1, C2, and C3 here are the corresponding ciphertext blocks for P1, P2, and P3. Note that depending on the block cipher, there will be certain number of round keys generated from this symmetric key right here. So essentially, inside this rectangle, we are doing the encryption on this plain text block. Similarly, for decryption in ECB mode, you first split your ciphertext into blocks of equal size. So we have C1, C2, and C3, for example, here. Then you take each ciphertext block and decrypt it separately using the same cipher key that you used for encryption to get back your plain text blocks. So you will get P1, P2, and P3 correspondingly for C1, C2, and C3. And so here, one thing to note is that we are encrypting and decrypting each block separately, so they are independent of each other. Now, there are some weaknesses with the ECB mode. For instance, if 2 plain text blocks have same data, their corresponding ciphertext blocks will also be the same. As you can see in these images here, the plaintext image here on the left has several repeating blocks. For instance, the white portions here, you can see they are the same. So if we divide them into blocks, they have the same content. Similarly, the yellow portions here, as well as the black portions here. Therefore, the corresponding ciphertext of this image will also have repeating blocks, because these plain text blocks, which have same content, will map to same ciphertext blocks. So it is possible to make inferences about the plain text, as in this case, we can still make a guess about what the image content is. Secondly, if a message encrypted using ECB mode is highly structured, it may be possible for a crypt analyst to exploit this. For instance, if it is known that the message always starts with certain predefined fields, so when should we use ECB? Well, we use it when our plain text size is small. In other words, when the data length is equal to or less than 1 block. Therefore, we typically use it to send small pieces of data such as keys or initialization vectors, which are usually 1 or 2 blocks. So to overcome the deficiencies of ECB, other modes of operations were proposed for confidentiality. One of these is the cipher block chaining, or CBC mode. Now, the CBC mode produces different ciphertext blocks for repeating plain text blocks. So now if we have P1 and P2 which have the same content, then C1 and C2 will be different. This figure shows encryption using a block cipher in CBC mode. Here, each plaintext block is chained with the previous ciphertext block using an XOR operation. And the output of this XOR operation is what is encrypted. This way, each ciphertext block depends on all plaintext blocks processed up to that point. So now, even if plaintext blocks P1 and P2 are same, then C1 and C2 will be different because of this chaining effect. And now, since there is nothing to chain with the first block, P1, we use what is known as an initialization vector with this first block. So we essentially chain the first block with an initialization vector. So the length of the initialization vector is the same as that of the plaintext block or the ciphertext block. So this initialization vector is known to both the sender and the receiver, and usually we protect it. So once the symmetric key is exchanged, the initialization vector can be exchanged by encrypting it using block cipher in ECB mode, which we just talked about. So pause here and find out the ciphertext for this plaintext using CBC mode, assuming the following information about the block cipher, block size, number of blocks, key, and initialization vector. So let's take a look. Here our plaintext is 111010011. And it says here that our block size is 4 bits. So we are going to split our plaintext into blocks, each of 4 bits. So our first block will be 1110, and our second block will be 1011. And it says here we have 2 blocks. And then our key is 1110, and our initialization vector is 1011. So let's try to encrypt each plaintext block using this information. So I will write the plaintext 1 here, just 1110. And the first thing to do is to chain the plaintext block with the previous ciphertext block, but because we don't have any ciphertext block for the first plaintext block, so we use the initialization vector. So here basically we are just going to XOR these two together. So I'm going to use the space right here to XOR these two. So we get 0, 1, 0, 1. This is the output of this XOR function. Now we're going to take this key and the block cipher encryption algorithm to encrypt this output. And because this is a very simplified example, our block cipher encryption algorithm is simply just XORing the block with the key. So we're not really doing multiple rounds and multiple round keys with each round, with multiple substitution and permutation steps. All we're doing is just taking this block right here and doing an XOR of that with this key. So let's do that. We have 0, 1, 0, 1 and 1, 1, 0. We XOR them. We get 1, 0, 1, 1. So basically the output here is 1, 0, 1, 1. That is essentially our first ciphertext block. Now we are going to chain this ciphertext block with the second plaintext block. So our second plaintext block is 1, 0, 1, 1. So we XOR these two together. We essentially get all zeros because both values are same. So all zeros is what we will actually encrypt, again using this key 1110. Because this is a symmetric encryption scheme that we're doing here using this mode of operation, the key has to remain same for each block. And this key essentially is what we split into multiple round keys inside this block cipher. So again, I'm going to perform encryption on this output block with this key, which is essentially just XOR operation, right? So all zeros XORed with 1110 essentially gives us 1110, which is our ciphertext block 2. So our ciphertext is 1011 1110. This figure shows decryption using a block cipher in CBC mode. It is essentially a flipped version of the encryption in CBC mode. Now we first decrypt each ciphertext block using the block cipher decryption algorithm and the same key that we used for encryption, and then we take the plaintext and chain it with the previous ciphertext block, just like we did in encryption. So we XOR the plaintext block with the previous ciphertext block, as you can see over here. This is because this was the first step that we did before we did encryption of each plaintext block. And so again, because there is no ciphertext block to XOR with the first plaintext block, we are going to use this initialization vector. And this is the same initialization vector that we used in encryption. And then for block 2, once we do the decryption, we are going to chain the output with the previous ciphertext block, and so on. So in summary, in CBC mode, a ciphertext block depends on all blocks before it. And any change to a particular block affects all of the following blocks. Therefore, if there is any error in one block, it can affect all subsequent blocks. This also makes it useful for integrity checking. The CMAC mode is based on CBC mode to calculate a message authentication code, essentially to check integrity. And what we do is we essentially encrypt plaintext using CBC mode and just take the last ciphertext block as our hash value or authentication code. Now CBC mode does need an initialization vector which must be known to both sender and receiver, and it must be encrypted in ECB mode before the rest of the message. Now there are various modes of operation that makes it possible to convert any block cipher into a stream cipher, which means that we will just perform an XOR operation of plain text and the key to get our ciphertext, and similarly we will XOR ciphertext with the key to get back our plain text. This is essentially what we do in stream ciphers. So these three modes, the output feedback mode, the cipher feedback mode, and counter mode, let you operate any block cipher as a stream cipher. The output feedback mode, or OFP, converts a block cipher into a stream cipher because the encryption and decryption of plain text and ciphertext block, respectively, is just an XOR operation with the key stream. This figure shows how the encryption is done in output feedback mode. Here P1, P2, and P3 are plain text blocks, and C1, C2, and C3 are their respective ciphertext blocks. And so here we are using block cipher encryption not to encrypt the plain text because we're not passing plain text here. Instead, we are using it to create some output block, which we essentially just use as a key stream block. So to generate the key stream block for the very first plain text block, we encrypt this initialization vector. This is essentially just a block containing random data. So we encrypt it using the block cipher encryption algorithm and the symmetric key. This output is not the ciphertext, rather an output block that we consider as the key block for the first plain text block. And so we take that output and we XOR that with the first plain text block to get our first ciphertext block. In this mode also there is chaining involved. Here the output of the block cipher encryption in the previous iteration is fed back as input to the block cipher encryption for the current iteration. So as you can see over here, this key block that was generated, this is the output of the block cipher encryption, and this is what we feed back to the next iteration. So again, this output is going to be encrypted again using the same key to give another output block, which is key block 2, which we will use to XOR with plaintext block 2 to get ciphertext block 2. Although we are chaining the blocks here as well, unlike CBC mode, the errors are not going to propagate. Why? Because we are not feeding back either the plaintext or the ciphertext from the previous block into the next iteration. In CBC mode, we were feeding back the ciphertext of the previous block. Here, we're just feeding back the output of this block cipher encryption algorithm. So yes, if there is any error at this point, it is going to impact the remaining blocks, but if there is any error in plaintext or ciphertext block, it is just going to impact that current block and not the next blocks. To decrypt using the OFP mode, we again use the block cipher encryption to generate a key block. In this case, the key block is used to decrypt the ciphertext block. Again, to generate the key stream block for the first ciphertext block, we encrypt the initialization vector block using the block cipher encryption algorithm and the key. And that is one of the reasons why we need to again use block cipher in encryption mode and not decryption mode, because we want to generate the same key blocks at the receiver end as well. Because we're not really using block cipher here for encryption or decryption, we are just using it to give us some new output. right? So we are going to take this output block as the key block and XOR that with the first ciphertext block to get our first plaintext block. And again, since chaining is involved, the output of this block cipher here, or the key block for the first ciphertext block, is going to be fed back for the next iteration. Again, note that although we are doing decryption using this mode, the block cipher is used in encryption mode since it is only being used to generate key stream block and not ciphertext or plaintext. Since we are operating block cipher as a stream cipher, encryption and decryption of plaintext and ciphertext respectively is just an XOR operation, as is the case in stream ciphers. So when to use OFP mode? Well, it is appropriate when data arrives in a stream of bytes. So the key stream generation steps can be computed in advance before the plaintext or ciphertext arrives, which can save some time. One difference from the previous mode is that the block cipher is used in encryption mode for both encryption and decryption, since it is only used to generate key stream blocks. And so since each plaintext or ciphertext block is encrypted and decrypted independently of each other, and they're not chained to each other, the error in one block does not impact the other blocks. The cipher feedback mode, or CFP, is similar to OFP mode in that it is also converting a block cipher to a stream cipher, and the plaintext or ciphertext is encrypted and decrypted respectively using just an XOR operation. However, there are several differences. First, we are chaining the ciphertext of the previous iteration to the next iteration. In OFP mode, we were feeding back the output of the block cipher, but here we are feeding back the ciphertext of the current iteration to the next iteration. Second is that the key block can be of various sizes in CFP mode, unlike OFP mode where it was fixed and equal to that of the plaintext or ciphertext block. So the S over here represents how many bits we want to encrypt at a time. So it can be 1 bit, it can be 8 bit, it can be 64 bits, or 128 bits. So there are 4 variants of CFP, known as CFP1, CFP8, CFP64, and CFP128. So let's say if we are using CFP8, we are going to use S is equal to 8, which means that we will have our P1 equal to 8 bits, and then we are going to XOR it with a key block that is also going to be 8 bits. So in encryption using CFP mode, we start with the initialization vector and encrypt it to get a key block, just like we did in OFP mode. Right, so this is basically the key block that we got just like in the OFP mode. Then depending on how many S bits we want to encrypt at a time, we will select that many bits from this key block and discard the rest. Right, so let's say if it's CFP8, we're going to select the first 8 bits and we're going to discard the remaining 128 bits. For instance, if we were to use AES, it is going to give us 128 bits. We'll take the first 8 bits and discard the remaining 120 bits. So then this is 8 bits, and then we XOR that with 8 bits of plaintext to get, again, 8 bits of ciphertext. And these 8 bits are actually what is fed back to the next iteration. And so notice here that we are feeding back 8 bits to the block cipher encryption algorithm, but this block cipher expects a block of, let's say, 128 bits. But here we are feeding back just 8 bits. So how do we get the remaining 120 bits? The way we do that is by taking the initialization vector that we had in the previous iteration. So we left shift it by s bits. So for example, in this case, let's say we have s is equal to 8. We left shift it by 8 bits. Then we add the bits from the previous ciphertext block into the last s bits here. So this will give us 128 bits, and then we encrypt it again using the block cipher, and we get back again 128 bits. So again, we're going to take the first 8 bits, again assuming that we have s is equal to 8, and then we discard the remaining 120 bits and use that to encrypt the next 8 bits in the plaintext. This ciphertext is then again going to be fed back to the next iteration. In the decryption using CFP mode, we again start with the same initialization vector that we used in the encryption process and encrypt it to get our key block. And then depending on how many ciphertext bits we want to decrypt at a time, we will select that many bits from this key block and discard the rest, just like we did in the encryption process. And these key bits will then be XORed with the first ciphertext block to give our first plaintext block. And so, because in encryption process we fed back ciphertext of each block to the next iteration, so again we're going to do the same thing here. And what we will do is we will take the initialization vector from the previous iteration, left shift it by s bits, and then add the ciphertext bits in the last s bits of this initialization vector. So this will give us an initialization vector which is different from the previous iteration. We then encrypt this block again to get a new key block, and again we take s bits from there, discard the rest, and use those s bits as key bits for the next ciphertext block. And we get back the next plaintext block, and so on. Just like the OFP mode, the CFP mode is used when the data arrives in stream of bytes. Also, just like in OFP mode, the block cipher is used in encryption mode for both encryption and decryption, since it is only used to generate a keystream block. However, here the keystream generation steps cannot be computed in advance because of the ciphertext chaining. And because of the ciphertext chaining, if there is an error in one plaintext or ciphertext block, it is going to impact the subsequent blocks. Next, we have the counter mode, or CTR. This mode looks very similar to ECB mode in operation. Here we split our plaintext into blocks of equal size and encrypt each block separately using the same block cipher encryption algorithm and the same key, just like we did in ECB. So we have parallel encryption going on for each blocks, and there is no chaining. There are, however, two differences between ECB and counter mode. First is that unlike ECB mode, in counter mode we use a counter value whose length is equal to the plaintext block to ensure that the same plaintext blocks don't generate same ciphertext blocks. If you remember, in ECB mode, that was the weakness, that if we have same plaintext blocks, their ciphertext blocks are also going to be the same. So here we prevent that problem by having different counter values for each block. So the counter is typically initialized to some random value known as nonce, and then incremented by 1 for each subsequent block. Second difference from ECB mode is that the counter mode can convert a block cipher into a stream cipher, as you can see here. This figure shows the encryption using block cipher encounter mode. Here we need to first generate a key stream that can be XORed with the plain text blocks. To generate this key stream, we first encrypt the counter value using the key and the block cipher encryption algorithm. And then we XOR this output, which is our key block, with the plain text block to get the ciphertext block. And we repeat this process for all the subsequent blocks. And for each block, the only thing to keep in mind is that we will have a different counter value. Here also we can actually perform some of the steps in advance. So if we draw a line here, all of this process can be done in advance because it is not dependent on the plain text or ciphertext. All we need is these counter values which we encrypt to get our corresponding key blocks. This figure shows the decryption using block cipher encounter mode. Again, here we need to first generate a key stream that can be XORed with the ciphertext block. To generate this key stream, we first encrypt the counter value using the secret key and block cipher encryption algorithm, and then we XOR this key stream with the ciphertext block to get our plain text block. And for the subsequent blocks, we will repeat the same process. However, the counter values are going to be incremented by 1. Note that although we are doing decryption, the block cipher is used in encryption mode here as well. Because again, this is only being used to generate key stream and not ciphertext or plain text. So the counter mode has several advantages over other modes. First one is efficiency. This is because each block is encrypted independent of each other. So we can do parallel encryptions and decryptions in hardware and software. We can also pre-process some of the steps before the plain text or ciphertext arrives because those steps are only used to generate the key stream and only needs counter values and not the plain text or ciphertext. This makes it helpful for high-speed links where fast encryption is required. Again, since each block is encrypted separately and is not dependent on the previous blocks, therefore the errors do not propagate. It only affects that current block. Let's look at the CBC-MAC or CMAC, which is used when we are only using the block cipher to calculate authentication code to check integrity of messages. So the cipher blockchaining message authentication mode, also known as CBC-MAC or CMAC, is a technique for constructing a message authentication code or a hash value from a block cipher. So essentially the message is encrypted with a block cipher algorithm in CBC mode, which we just looked at. The reason why CBC can be used for authentication is because each block depends on all the previous blocks. This interdependence ensures that a change to any of the plaintext blocks or ciphertext blocks will cause the final encrypted block or decrypted block to change in a way that cannot be predicted or counteracted without knowing the key to the block cipher. So this figure shows how to calculate the CBC-MAC for a message M. So just like we discussed in CBC mode, you would take your message M and you would split it into blocks, M1, M2, and so on, which are all of equal size, which of course is defined by the block cipher that we're using here. But one thing to note is that all of these blocks will be using the same block cipher. Then you encrypt these blocks in CBC mode. And for the first block, since we use an initialization vector, here we use an initialization vector which is essentially a block consisting of all zeros. So here for the first block, we chain the initialization vector with the message block by doing XOR, and its output is what is going to be encrypted, which will give us the first ciphertext block. And we chain that ciphertext block with the plaintext block 2, M2, again using an XOR operation, which we again encrypt. We get C2, which we again chain. So it's cipher block chaining. And then we do it for all the blocks. And for the last block, whatever ciphertext we get, which is Cn in this case, is what we take as our hash value or message authentication code. Now there are several modes of operation that offer confidentiality as well as authentication of messages using block ciphers. Let's look at two of these combined modes that offer both, namely counter with CBC-MAC, which is known as CCM, and Galois counter mode, which is known as GCM. So counter with CBC-MAC or CCM is a mode of operation for cryptographic block ciphers that is designed to provide both authentication and confidentiality. As the name says, it combines the CBC-MAC mode with the counter mode. So we use the counter mode for confidentiality and the CBC mode for authentication. The CCM mode is used in Wi-Fi security protocol WPA2. It's also used in IPsec or IP security, transport layer security version 1.2, as well as in Bluetooth 4.0. It is available for TLS 1.3, but is not enabled by default in OpenSSL. So first, the CBC-MAC is computed on the message to obtain an authentication tag, because we said that we are using CBC mode to calculate authentication code, and we're using counter to calculate confidentiality or ciphertext. So if you look at this area within this red rectangle, this is essentially depicting the CBC mode, where we chain the ciphertext blocks together. So we take our plaintext block, XOR it with the ciphertext of the previous block, and then the output is what we encrypt. And then we chain that again. And again, for the first plaintext block, because we don't have any ciphertext, we use what is known as an initialization vector. However, here, instead of seeing one initialization vector, we see some additional blocks. These A blocks are any additional data other than the plaintext that we would want to authenticate, such as header information. We might have these or we might not. And so this is essentially our initialization vector, which is just a nonce, number only used once, and length of the plaintext concatenated together. So this whole block is our IV. So we take its ciphertext and not its plaintext and chain it with the first authentication data. We encrypt that, we chain it again with the next authentication data block, and so on. And then the ciphertext for the last authentication data is what we chain with the first plaintext block. And then we keep doing that. So then once we have encrypted the last plaintext block using the CBC mode, we take its ciphertext block, and this is what is our MAC. And this is essentially CBC-MAC that we just looked at. And this area inside this rectangle is depicting the counter mode, which we just looked at. And this is being used here for encrypting the plain text for confidentiality. So as you can see here, we're using a different counter for each block. We're constantly incrementing the counter from the previous block. And we encrypt the counter, we get back a key block that we just XOR with the plain text block to get our ciphertext block. And then we do that for each plain text block independently of each other because there is no chaining in counter mode. And you can see over here on the left that we keep the first counter value essentially to encrypt our message authentication code that we just calculated using CBC mode. So what we're doing here is we're taking the first counter value, we are encrypting it, we get our key block 1 as 0, and we take that key block 1 and we XOR it with the MAC that we just calculated using CBC mode. This was essentially ciphertext M for the last plain text block. And then we XOR them together. We get our encrypted message authentication code, also referred to as a tag. And we could actually just take first X number of bytes from this encrypted block, which we can use as our tag. The Galois counter mode, or GCM, is one of the more recent modes of operation, and it is used in a number of protocols and standards because of its performance. For example, it is used in TLS, SSH, IPsec, OpenVPN, and Ethernet security. GCM uses the counter mode for confidentiality, just like CCM. However, it uses a new Galois mode for authentication. This portion in red is showing you the counter mode for encrypting plain text block, and it is essentially the same as what we saw in the previous slide for CCM. So we have counter values that we constantly increment for each block. We encrypt the counter value, we get a key block, and then we take our plain text block, we XOR these two together, we get ciphertext block. This is essentially counter mode. And here as well, we are keeping the first counter value to use for our authentication code. The authentication tag in GCM is calculated on the ciphertext instead of the plain text, as you can see here. In CCM, we are calculating the authentication tag on the plain text. However, in GCM mode, we are calculating the authentication tag on the ciphertext. Now, the Galois field used here is 2 raised to power 128, where 128 is the size of each element. So because we have 128-bit blocks that we use in AES, so the size of each element is 128 bits. And then 2 over here just means that when we convert each element to a polynomial, we can only have 2 possible coefficients, which is 0 or 1, and which makes sense because we are working with binary data. And over here, Mult-H basically means multiplication with H. And what is H? H is essentially just a string of 128 0 bits encrypted using the block cipher. So it is essentially a block. So when we say mult-H, we actually convert H block to a polynomial, and the other data block being multiplied with it also into a polynomial, and then we multiply them together. And if the result is larger than 128 bits, then we reduce it to make it 128 bit. And how do we reduce it? We reduce it using this reduction polynomial, which is specific to this Galois field right here. So again, we convert data blocks to polynomial, we multiply those polynomials, and if the result of the polynomial is a bigger polynomial, in this case, we can only have each term with a degree of 127 or less. So if after multiplication we have 128 or larger, then we have to reduce it by doing a modulo operation on that multiplication result with this reduction polynomial. That's essentially what this mult-H over here means. So here also we start with any additional data that we just want to authenticate and not encrypt for confidentiality. What we will do is we will multiply it with this H block. So essentially that means that we're going to convert this data into a polynomial, we're going to convert this H block into a polynomial, we're going to multiply them, and then convert their result back into a 128-bit block. And if it's larger than 128 bits, we have to reduce it. And so that result, 128 bits, is what is XORed with the ciphertext block. And then the result is again multiplied with that H block, and then it is chained with the next ciphertext block. So essentially this is using CBC mode, where you can think of this result of multiplication H as your ciphertext block, which is being chained to the next plaintext block. Here actually the plaintext is the ciphertext block. After the last ciphertext block is processed, the length of additional data that we used here is appended with the length of the ciphertext, which we are doing the authentication tag on. That is XORed with output of the last ciphertext block. And then it is again multiplied with the H block, and that output is XORed with that first key block that we generated using the first counter. And that is what gives us the authentication tag.